on the simplicity of axiom systems and of proofs. And the first part is something that I have been interested in at the beginning of my career, so kind of like the first 20 years. And the simplicity of proofs, while I was interested in, I haven't been able to produce results until recently, which is about 4 years ago. So let's see what the problems are. So first of all, the problem of simplicity has been rather old. In his Wissenschaftslehre, Bolzano tells us that this problem seems to me to be so difficult, and the attempts that were undertaken so far for its solution so unsuccessful, that I have no desire to dare another one. So people have been aware of it and have been aware that it's not easy to figure out what simple is. In 1935, there was an International Congress of Scientific Philosophy in Paris. And out of the 8 contributions that were printed, 3 were devoted to simplicity. Nowadays, it's rather rare to find any such interest, to say nothing at a major Congress of Scientific Philosophy. So, how do we go about this? I mean, where do we start? Well, one place to start is language. So in other words, if you have an axiom system, well, you're going to have a language in which to define it. And as we know, unless we are Frege, there is a vast variety of languages in which we can express the same thing. And there are many papers that tell you what the same thing is. Because the same thing is not as easy as saying that 2 theories are synonymous, because in one language, the individual variables may be completely different from the other one. So how do they communicate? Well, there are ways to translate and to say that they're saying the same thing on a semantic level and on a syntactic level. So you can actually define what those translations look like and so on. So deciding on the language is one thing that would be in the area of simplicity. Now, there are 2 kinds of simplicities. One is relative simplicity. In other words, this thing is simpler than another thing. And the other is absolute simplicity, which means this is simplest regardless of what you will ever come up with. I'm interested in the second, not interested in relative simplicity, because in relative simplicity, tomorrow somebody comes and beats you. With absolute simplicity, you're certain. So, for example, in relative simplicity, you would say that, well, language-wise, if you look at the language of Tarski that we've seen in the past, which was just point as individual variables, and 2 relation symbols, a ternary one for betweenness and a quaternary one for equidistance, is simpler than Hilbert's, where you have points, lines, planes, betweenness, incidence, segment congruence, angle congruence. So obviously, you see that the individual variables and the relation symbols in Tarski are a strict subset of the ones in Hilbert. So certainly that's simple. But how do you go about absolutely if you don't have to compare between 2? You compare yourself with any possibility. Well, you would like to have as few symbols as it gets. And the symbols that you have, you want them to have minimal arity. So arity means what? I mean, it's, it's a binary symbol, a binary, say, relation is easier than a ternary relation. And a ternary is easier than a quaternary. I mean, it's simpler. And obviously there is a problem. How do you compare the simplicity of ternary relation and a ternary operation, for example? They're different animals, you know? So, because an operation is in fact a hidden relation with one more term. So, okay, if you have those, then you have to figure out a way to do it. But in principle, the fewer you have, the better the things are, the fewer and the smaller. So preferably, if you could have just one that is unary, would be great. Only we know that just one that's unary can't say much of anything. So that we know. So basically, you would have to have at least binary. So if you ever manage to get just one binary relation, then you're on top of the mountain of simplicity. Okay, so suppose you decided now on the language. We live in just one language. Then you want your individual axioms to be as beautiful as they can be. Well, what's one of these beauty criteria? Well, we don't like lots of quantifier alternations, you know. If you wonder, like, why is analysis complicated to students? It's because you have quantifier alternations for the first time in your life, you know. Until then, everything was universal. And now you have for all there is for all, you know, all those definitions, you know, which we avoid in the United States. We teach calculus as if there was no quantifier whatsoever. That simplifies things. So, so you want simple quantifier complexity. So what does simple mean? Well, the best world is to have only universal quantification. Don't have any quantifier. The next best is universal existential. The next best is universal existential universal, and so on. So that's what you want. Now, after you're done with your quantifier complexity beauty criterion, now you have how many variables do I use in these axioms? No? I mean, you have a theory. Now you have decided on the language. It lives there. It doesn't move at all. Inside that language, what is the most complicated axiom that I need to assume? Complicated in terms of numbers of variables. That's going to be called the simplicity degree of this theory. So if I have to have an axiom with k variables, I can't do it with k minus 1 in any possible way, then the degree of simplicity of that theory is k. Okay? I guess by this place, it sounds familiar with something that you heard on the Pasch axiom talk, because there we were wondering if it is possible at all to replace Pasch's axiom, which is a 6-variable statement, by some 5-variable statements. And we've said this is an open question. We have 15 different 5-variable statements that are saying stuff in ordered geometry, and we don't know whether they collectively imply the Pasch axiom or not. If they do, then the simplicity degree of ordered geometry would be 5, else it is 6. Okay, so how do these things look in a familiar setting? So we are in Tarski's language, let's say, and we want to check all of this simplicity story in it. So what we have is this ternary relation for betweenness and the quaternary relation for equidistance. And what are the Euclidean geometries that we will be looking at? One is the Euclidean geometry of ruler and segment transporter construction. So I can take a segment from somewhere and move it somewhere else. And the other one is the geometry of ruler and compass constructions. So in other words, I know that a circle and a line that has a point inside and one outside, they do intersect. So in one case, the coordinatizing field is Pythagorean ordered, which means the sum of any two squares is a square. And in the other case, it is Euclidean ordered, which means any element is either a square or the negative of a square. Now, the simplicity degree of n-dimensional geometry over Euclidean fields is 5 for n is 2. So in other words, plain Euclidean geometry can be axiomatized by axioms, all of which have at most 5 variables, which means we can beat Pasch, right? Why can we beat it? Because the circle axiom implies Pasch's axiom, and the circle axiom asks for fewer variables than Pasch. And for n greater or equal than 3, it's n plus 2. Now, n plus 2 is absolutely top. Why? Dana Scott in 1959 in this conference that was at Berkeley, I mean, it was in 57, 58, but it was published in 59, which was published under the name the axiomatic method, has shown that any axiom system for n-dimensional Euclidean geometry would have to have an axiom with n plus 2 variables because of dimension. You can't express dimension in less than that if your language has just points. Yeah? So for n greater or equal than 3, the stuff we get in Tarski's language is absolutely optimal. All axioms are universal existential, which is optimal because, well, in a language with just relation symbols, you don't expect with just universal to get anywhere, right? Just tells you nothing. It's great in the universe of one point, everything you're saying. So now, for two-dimensional hyperbolic geometry, the simplicity degree is also 5, and all axioms are universal existential. You'd ask yourself, how is it possible? Don't you have to deal with something like the transitivity of the equidistance relation? I mean, how do you do that? Well, this is the biggest headache, to tell you the truth. It's an even bigger headache in hyperbolic geometry. It takes about 5 pages of headache. And it took me half of my sabbatical at the time, my first sabbatical. Because what you're doing is you're expressing this thing for 5 variables. So you don't have EF, you have, the A, B, C, D, and then E, but no F. Yeah? And then you have one of the old ones. And you have several of these, like 4 or 5, and you have to somehow, out of those, to get this general one by using many other things that are completely crazy. And as I said, in the Euclidean case, it's, well, only 2 pages. In the other case, it's much worse. So this is the hard work that, we have to do to get there. There's some other technical things, but this is the worst, Okay, so we know that in Tarski's language, in two-dimensional, you could do universal existential, and you need 5 points for both of these. They're not absolutely ideal, Because in Dana-Scott, according to Dana-Scott's theorem, all you need is a theorem that speaks about 4 points, right? Now we have to have theorems that speak about 5 points, but that's because our language is, well, this language. Perhaps there is a more incredible language. We haven't found it yet. Nobody knows if there is any language with just relationship symbols where you can get by with 4. You probably can't. Well, you could ask these kinds of questions in Robinson's Q, for example, in arithmetic. You know. Is there a theory that is equivalent to Robinson's Q where you get by with just 2 variables? Nobody knows. Probably not. So, in the case of Euclidean geometry over Pythagorean ordered field, we don't know what it is. It's either 6 or 5, depending on whether you can replace Pasch by other things which are now helped by the congruence axioms to get somewhere. That's not known. The same if you want to go for other things. For example, you can have a Euclidean geometry that is just over ordered fields, arbitrary ordered fields. What's the simplicity degree of that? We don't know. Same in the hyperbolic case over ordered fields, which is these generalized hyperbolic planes, which were introduced by Klingenberg. Also unknown is what do you do if you just have congruence and you just want to say the basic structure of the Euclidean plane. So in other words, Euclidean geometry over arbitrary fields of characteristic different from 2, in which there is an element that is not a square. In these, you can generalize the idea of the complex field and create a geometry of just distance. What is the simplicity degree of that? It's not known. Now, if you allow ternary operation in this story, then the simplicity degree drops to 4, which is this super ideal thing that you can't do any better. And this is for a wide variety of Euclidean geometries with or without order. And same is with hyperbolic geometry. The axiomatizations in terms of ternary operations are quantifier free, so they're the absolutely simplest imaginable. So they fit 3 simplicity criteria. It's least amount of variables, right? 4. Least quantifier complexity, everything's universal. And the language is the simplest because it contains just ternary operations. And we know from a theorem of Engelen in 1983 that even if you allow for quantifiers, you can't express Euclidean geometry just by binary operations. Yeah. So, and you can also prove that the operations themselves are both needed, and there are 2 in general in all these things, and that you can't get rid of one. So here we got to the top of simplicity. You have simplicity in every sense. Now, let's look at other languages. So we stayed somehow with Tarski, then we move to a language with ternary operations. Now, the oldest analysis of simplicity comes from Pieri, again, because he was actually the first person to deal with mathematics in this manner. We remember what I said the first time, it's that at the thesis defense of James Smith at the University of Regina in Saskatchewan, Tarski was present. The advisor was Gupta. And Tarski asked the doctoral candidate, well, where does this field originate? And Jim answered it's in Hilbert's Grundlagen der Geometrie. And Tarski said, no, it's wrong. It's in Pieri. Because indeed, the kind of logical analysis of geometry does not occur in Hilbert in the same manner that it does in Pieri, who's interested in the formal aspects of things. So what Pieri did in 1908 was to show that Euclidean geometry over Euclidean ordered fields can be axiomatized in terms of just one ternary predicate. This isosceles predicate, or, well, it's A, B, C are in this relation if A, B is congruent to A, C. So you can call it a kind of equidistance among 3 points, not 4, as we have it in Tarski. And this we know is absolutely simplest in the sense that Raphael Robinson showed in the same conference, 1959, that Euclidean geometry, even if you add a finite number of fixed distances to the language, so suppose you have a unit distance and many more distances that you have additional axioms for, you can still not axiomatize it with binary relations only. So a ternary relation is a must. And what Pieri says is that just one ternary relation is enough. Now, recently means about 100 years after this appeared, people have realized that there is a price to pay, apparently, for the simplicity of the language. Because if you were to express Pasch's axiom, for example, which you need in this world, in terms of Pieri's I, then one would get a for all there is sentence. That would require more than 15 lines and 300 characters. Wow. It turns out that things are not as bad. You can get by with a universal existential axiom system in terms of Pieri's relation for a wide range of geometries. You have to not go by the path of, let's look at, say, a system like Tarski's or Hilbert's, and then express it in terms of I. You have to start completely different. You have to start with an axiom system for metric planes, those things that I've introduced a long time ago, the Bachmann things. And then you can build upon them. You can say the metric is Euclidean. Then you get Euclidean geometry over Euclidean ordered fields. And you get absolute geometry with a circle axiom, and you end with this Klingenberg generalized hyperbolic geometry. So the theory is not as monstrous as it appears. So from the point of view of quantifier complexity, it's the easiest that you can get. There is an axiom system that is universal existential. Now, what about the simplicity degree of it? Well, nobody knows it. So in other words, how many variables does an axiom of the best axiom system imaginable for Pieris geometry have to contain? We don't know. Now, sometimes what happens when you have a lower arity relation is you do have to pay. I mean, here we didn't have to pay anything, you know. We dropped from this quaternary relation plus the ternary relation to just one ternary, and we didn't have to pay anything in terms of quantifier complexity. Is this always the same? No, it's not. Example. Well, Wanda Schmierle has shown in 1983 has a, well, in fact, Maria Moszinska has published in English the notes that Wanda Schmierle left on affine geometry in terms of the quaternary relation of parallelism. So you have AB parallel to CD means that, you know, this line, the line formed by AB is parallel to the line formed by CD. So you have just points and just this quaternary relation. And that axiom system is universal existential. If you express it in terms of parallelism, it's universal existential. If you express it in terms of just collinearity, which is a ternary one, right? A, B, C are collinear. Then it is universal existential universal. And you can't express it as a universal existential theory in any way, which is what Wanda Schmierle has shown in this book that was published in English in 1983. The Polish original was published sometimes earlier, probably 79 or so. So it's not, the moral of the story is that sometimes if you want to be better in one way, you pay a price. So if you don't like quaternary relations in affine geometry and you want to go ternary, then you're going to pay a price in quantifier complexity. You can't have it all the way we have it in Euclidean geometry, where it seems like we can drop everything and everything stays beautiful. In the Pieris case, you know. Now, Pieris relation hasn't been the only one. In 1956, there was a series of papers in Indagaciones Mathematicae about other ternary operations. Well, one is in a paper by Tarski, this J operation, which is a relation, like another ternary relation, which says the distance between x and y is less than the distance between y and z. And it can serve as single primitive notion for Euclidean geometry over Pythagorean ordered fields of any dimension greater or equal to 2. And a symmetrized version of I can replace I. I is Pieris, and now you're saying in any order x, y, z, so h of x, y, z, if x, y, z are in any order in the I relation. And they're not equal. No, so there are at least 2 are different. So, because the question was, there is a beauty deficit in Pieris relation, and that is that it's not symmetric. So you have I of ABC means AB is congruent to AC. So it matters how you write your 3 variables. Can we get a relation that is symmetric was the question at the time. And it turns out that, well, J isn't symmetric, but H is. So yeah, you can get, and there will be more symmetric ones. In the same journal, Dana Scott in 56 has shown that another ternary relation can serve for Euclidean geometry over Euclidean ordered fields of any dimension that is greater than 2 is the ternary relation that says x, y, z are in this relation if they are in any order the vertices of a right triangle. And Beth and Tarski in the same journal have shown that the relation E, where XYZ is an equilateral triangle, can serve as a primitive notion for the Euclidean geometry of ruler and compass constructions in any geometry that is at least 3. Now, let's look at another single ternary relation that works as single primitive notion for a geometry. If we look at hyperbolic geometry, then Menger showed in 1938, and then there was when he went to the University of Notre Dame, he found students who simplified his axiom system. And by 1946 or so, it was already in a very nice shape. And then later on, Helen Scala, one of his students in 1993, published an even more simplified version. People still are working on, Kim Pentila told me that he's still working on a further simplification. So the interesting thing is that hyperbolic geometry is an incidence geometry. It can be axiomatized just in terms of collinearity. Euclidean geometry certainly can't. If you have, with L, you get just affine geometry. In affine geometry, you don't know how to compare length on different lines. On the same line, you can say, you know what this is, because you can do things with parallelograms and say that they use some form of disargent to say that they have the same length. But to say that two things on different lines have the same length is impossible. Or put in group terms, the affine group is much larger than the orthogonal group. So he claimed that for this reason, hyperbolic geometry is simpler than Euclidean geometry, because he thought that independently of the fact that Euclidean geometry is also axiomatizable in terms of a ternary relation, the kind of relation that hyperbolic geometry allows is intuitively very simple. Collinearity seems like a very simple thing. The formal system doesn't know that it says that and doesn't know that it's simple, but still he thought that that's a case for the hyperbolic geometry being simpler than Euclidean geometry. So then I looked at this statement to see if it holds water. And I could show that that's not quite the case. If we express hyperbolic geometry in a traditional manner, because hyperbolic geometry, how did it come about? Came about in the first half of the 19th century by people trying to find whether you can have the parallel postulate denied, but kind of everything else in place. And the everything else was absolute geometry. Well, absolute geometry has something to do with being able to measure distances. So the traditional way it appeared was not as an incidence geometry, but rather as a geometry of betweenness and equidistance, if you want to put it anachronistically in that way. And as a theory of betweenness and equidistance, it is a universal existential theory. These are also called inductive theories, but that doesn't concern us now. Yeah. But if you express it in terms of, yes.
The term.
My microphone here, yeah. Mm-hmm.
The term hyperbolic geometry, as I understand it anyway, it only becomes ambiguous in four dimensions, I suppose. Because in three, as I said, the way I understand it anyway, you have minus plus plus and plus minus minus, which both correspond to the hyperbolic case. But then in 4 dimensions, you get the new case plus plus minus minus or minus plus plus minus. The 2 and 2, you may be understanding.
Yeah, you're meaning the metric, how you write it. No, we mean something very standard when we mean hyperbolic geometry. We're thinking of the interior in n dimensions, if we think, then the interior of an n-dimensional sphere, yeah, without the boundary, with a metric that can be defined. This was Menger's realization, in purely projective terms. So in other words, purely in terms of its incidence structure. So all of these have the same metric. You just add one more square because you're in higher dimensions. So what you're thinking about is more Cayley-Klein geometries in which you can vary those things. No, here we're talking about just this one thing. In every dimension, it behaves the same way. Yeah. So there is no difference here, and so depending on your model, what I described is the Beltrami-Cayley-Klein model, right? This internal. You can go by the Poincaré model where your lines, just in our model, the lines are just what you have inside that sphere, right? So these are the lines. And on those lines, how do you measure distances? Well, I could draw here how it works. So you can see that it's a purely projective story. Well, what should I do? First, let's get, I don't see where that is. How do you get this out of this? Here it is. Let's put this thing in. Let's see, can I do things right here? Let's do that. No, it works. Oh, beautiful. Yeah, we're here. Okay. So inside this circle is where our world is. And now I have 2 lines. Suppose the 2 lines are in a very, very special situation that the ends of the 2 lines, the one end is the same for both, right? In this special situation. And I happen to have this here and this here. I have 2 segments, and I'd like to know if they're congruent or not. Well, how do I do it? Well, I join this with this point here with the end of the other line. This point here with the end of this line. I get a point of intersection here. I do the same thing with these 2. Now, this is congruent to that if and only if these 3 points are collinear. Okay? So it is completely projective or completely in terms of collinearity. Now, what happens if I'm not lucky? So in general, you're not lucky. It's like this. These are 2 lines, and here you have a segment, and here you have another segment. And you'd like to know whether they are congruent or not. What do? Well, get one like this. Then if you find one here, which is congruent to this, now I know what congruent means because I defined it over there, right? And this is also congruent to this, then these 2 are congruent and we're done. See, in this case, the joining line is in the situation here, right? These 2 are exactly in this situation. So I know precisely what that means. And these 2 here, this and this, are also in the situation from there, so I can define it. So AB is congruent to CD here, if and only if there exists an EF such that the EF is congruent to AB and the EF is also congruent to CD. And this story is independent of dimension. You can go up and does the same thing because you're gonna look at this anyway in a plane. You're gonna somehow be able to reduce them. Even if your lines are like this, you could join this with that, and these two are in the same plane, and those two are in the same planes. Yeah. So, where are we? We need to get rid of this thing. Okay, and now I need to have a little more here. Okay, and do it. Okay. Okay, so yeah, you're dropping the complexity of your language because you have just one ternary relation, this collinearity. But this ternary relation now forces a much more complicated quantifier complexity of your system. So in other words, there is no axiom system in terms of collinearity that avoids having an axiom that is for all there is, for all there is. The simplicity degree of this L theory is unknown. So how bad must it be? The existing ones contain Pascal's theorem on about, to explain, you have to say somehow that your boundary is a conic. And how do you do that? Well, by saying that, you have a hexagon there, and every hexagon will behave like Pascal's theorem does. And so that asks for lots and lots of variables because you can't use just the 6 because the 6 will be ends. So to express that something is ends, you need more points. So it's something like, I don't know, 12 or so. So it's much, much worse. But nobody knows whether the simplicity degree is, but it is certainly higher than 5, what we had with Tarski's axiom system. So if you want it to be very simple in terms of the language and the meaning, here is the simplicity which is not formal, notice. It's a simplicity of the heart because we think that L is a very simple thing because we know it says nothing, it just says collinearity. It's almost nothing. Yeah, if your language was in terms of points and lines, right, and incidence of point and line, then this is just nothing. It's point lies on line. It's as if it were just set theoretical belonging. And that you can do anything with that is remarkable. But what I'm saying is that formally, we don't see why L is any different from Pierre's I, because it's still a ternary relation. So there is an added simplicity which comes from the fact that we are humans and we know what this means and we're surprised. The formal system doesn't know this, except for it tells you that you have to pay a price for the simplicity of your, which we didn't always have to pay. Sometimes you do, sometimes you don't. Now, plain hyperbolic geometry is better than Euclidean. In Euclidean, we've seen that there is no finite set of binary relations that can axiomatize. In hyperbolic geometry, and the same thing is true about binary operations. You can't do Euclidean geometry with binary operations only. Yeah? Who showed this? Engeler in 83. Okay? But hyperbolic geometry can be axiomatized in terms of the point reflection operation alone, which is a binary operation. You have 2 points, A and B. Sigma of AB is the reflection of B in A. This is all you need. So only with this notion, you can write your whole axiom system, and the axioms are all universal existential. If you don't like operations, you can replace this sigma by the midpoint operation. It's a ternary operation that says that, you know, M of ABC means that B is the midpoint of AC. And that also works. Equiaffine geometry, which is the affine geometry in which you can express it in terms of the group of transformations, are the affinities which preserve area. That can be axiomatized in terms of just the ternary relation delta, where delta means that the triangle, the area of triangle ABC is 1. Now, what if we move away from points? Everything we talked about so far was as if the only variables were points, as if points are kind of the subject matter of geometry. Geometry has this quality that is not shared by other things. I mean, I don't know what you do in groups, for example. In groups, you have just elements. You can't say, well, I have a group theory that is in terms of something completely different. Yeah, there's no such thing. In arithmetic, I mean, how do you change your variables? I don't know, you can't. It just, the variables are what they are. In geometry, you can. So we had points previously. Now we say, well, let's liberate ourselves from the chains of pointness and allow ourselves to have different variables or different interpretations. So the first that we will be looking at is what happens if we think that lines are our individual variables. Then you can axiomatize everything with a single binary relation. So Schwabhäuser and Szczerba have shown in 1979 that you need 2 binary relations. One is this perpendicularity, and the other is the intersection. Perpendicularity says that the 2 lines are perpendicular and intersect. Why do you need to say and intersect? Because they are in 3 dimensions, so it can be like this. No, you don't want those, you just want these. Huh? Okay, and the other one says that they just intersect too. With just these 2 relations, you can express all of 3-dimensional or higher dimensional geometries. In dimension 3, you can't do everything in terms of just orthogonality. You need the intersection one that was shown by Richard Kramer in about 1990. But if you go on dimensions greater or equal than 4, then perpendicularity alone suffices. What happens in hyperbolic geometry? In dimensions 2 and greater or equal than 4, you can get by with just perpendicularity. And with perpendicularity, you can do it with universal existential axioms. This is something I've shown in 2004. In dimension 3, again, things are bad. You can't get by with perpendicularity alone. It's an open question to figure out, both in Euclidean and in hyperbolic, what is the theory of orthogonality? Okay, it's not strong enough to give you the geometry, but how strong is it? So if you're in dimension 2 or dimension 4 or higher in the Euclidean case, you can get the simplest language that you could ever hope for. just one binary relation. You can't get any better than that. And the quantifier complexity doesn't increase from what it's supposed to be. I mean, you can't get below universal existential. Well, you have a universal existential one. What is the simplicity degree of these? Nobody knows. Projective geometry, how does that look if you work in a wall of lines? Again, Mario Pieri in 1901 has shown that one can axiomatize three-dimensional geometry in terms of line and the binary relation of line intersection. 13 years later, the axiom system was simplified to one that contains just 7 axioms, and one of them is a statement of 6 variables, the others are less. The quantifier complexity is universal, existential, universal. It appears like that the simplicity degree of this theory is 6, although nobody has proved that. So you need to show that you can't do it with just 5 variables. Much later, Trott has shown that you can do it with universal existential statements, but this time you need an axiom that speaks about 7 points. Again, it would be an interesting question to see if all universal existential axiom systems do require one axiom that has 7 variables. What about if we move away from lines and we allow circles, spheres, these to be our variables? So the pioneering paper here was in 1983 by Krzysztof Rażmowski, who showed that Euclidean geometry over Euclidean ordered fields can be axiomatized in terms of circles and circle tangency alone. I've generalized that to show that n-dimensional Euclidean and hyperbolic geometry can be axiomatized in terms of spheres and sphere tangency alone. So this is again as good as it gets, because you can't do better than a binary relation, right? And this time there is no more dimension in which it doesn't work. Remember, in Euclidean and hyperbolic, we had the dimension 3 that was bad. In Euclidean, you have the dimension 2 that also doesn't work. Here it works in all dimensions. Obviously, nothing like universal existential is not known. It's not known what the quantifier complexity is. It's not known what the simplicity degree is. I mean, how bad does it need to be? Because actually, what do you do with these things? You show that you can define points and the things that you have in your Tarski, say, system in terms of these things. We don't actually have nice axiom systems that people would say, oh, this is what it's saying. If you try to write these things down, they probably look awful. Nobody has actually. Huntington in 1913 has shown that you can do this thing with a binary relation that is even more dramatic. It just is the one of inclusion. In other words, your objects now are closed balls or solid spheres, and all you care is if one is included in the other. This looks like miraculous. I mean, how can you do it with something as general as this? And if it's too good to be true, then it is too good to be true, because the problem is you need higher order logic for this, right? The same problem is with a very short paper by Tarski in 29, where he did the same thing, Jaskowski in 48, and then it was taken over in a very long paper in the Bulletin of Symbolic Logic in 2008, where certain shortcomings in Tarski's paper and certain varieties that you can get if you interpret things in one way or another were pointed out. But again, nothing is in first order logic. These things are in monadic third order logic. Everything so far has been syntactic. So all these beauty criteria are, how does it look like to the eye? You know, I don't want lots of variables in my operations. I don't want lots of variables in my sentences. But these sentences can say very strong things, you know. On the other hand, when we make axiom systems, why don't we say, if you have a finite axiom system, you can just say one axiom. Take all the axioms, put end in between, you know, and you have just one axiom. Why don't we do that? Well, because we're interested in the contribution each axiom brings to the story. In that sense, you don't want to have strong axioms. You want to have as weak axioms as possible, so you see the contribution of every idea. And the ideas should be as small as they get. You should somehow be very stepwise in your construction of that theory. And so here is the only semantic criterion that I'm aware of, which is a very interesting one. And it has guided me in several of the things I've been doing, although I never found an axiom system that would be absolutely simple according to this criteria. So at this International Congress of Scientific Philosophy in 1935 in Paris, Olaf Hilbert produced the following criteria. You call an axiom in an axiom system, you say that an axiom in a certain axiom system splits into two other axioms if it is equivalent to their conjunction. Each of those axioms that you've split alpha into are weaker than alpha. Yeah? They're strictly weaker than alpha. And the axiom system without alpha does not prove alpha 1 or alpha 2. You've encountered this already in my previous talks, when we had the talk on the parallel postulate. We've said that the parallel postulate, we split it into the Loschnitt axiom and Aristotle's axiom. What did that mean? Well, the Loschnitt axiom independently is weaker than the parallel postulate. So is Aristotle's axiom. Taken together, they're equivalent to the parallel postulate. So the first two conditions are true. It's also true that it's not true that every model of absolute geometry would have to satisfy either the Aristotle axiom or the Loschnitt axiom. So this junction is not true in absolute geometry. Why do you need this third condition? The first two, you can think, okay, I understand them, they're nice. Why do you need the third one? Because if you don't put the third one, then people could come up with stupid splittings. Suppose alpha 1 is something weaker than alpha. And then instead of alpha 2, you're writing alpha 1 implies alpha. Then everything is true here. But the last one is not true. Because if you have alpha 2 means alpha 1 implies alpha, that's not alpha 1 or alpha. So in the last line, you would have alpha 1 or not alpha 1 or alpha. And that is logically valid. So it's surely going to be true in it. Okay, so what is the criterion then? Well, you call an axiom in an axiom system to be splittable if there exists an alpha 1 and alpha 2 in which it splits. And an axiom system is said to be semantically simple if none of its axioms is splittable. So in other words, each axiom says just the weakest idea that you can get there. It's not made of two distinct things, right? So none of the axioms is too strong. So if we go back and look at the parallel postulate, right? The parallel postulate is too strong. There's two completely distinct ideas that it's made of. It's the Lord-Schnitt axiom and Aristotle's axiom. Yeah? So why would you say it as such? It makes no sense. Say the steps that it's made of, the individual thoughts that are weaker. Now it's possible that the Lord-Schnitt axiom has two like this. Will you ever come to some place where you can't split it anymore? Nobody knows if there is such a thing. But it at least offers a semantic ideal of the direction you should be following. And you've seen several splittings already. You've seen the splitting of, we've said that inner Pasch is weaker than outer Pasch. So what do I need to get from inner Pasch to outer Pasch? What's the missing link? The missing link is the alpha 2. And so you can use this as kind of a guide. Whether there will ever be a semantically simple axiom system, we don't know, but at least we can look at that as an omega point in Teilhard de Chardin's rule, right? Now we're done with simplicity of axiom systems, and we're looking at simplicity of proofs. So this is something I have been interested in more recently. I mean, I've been interested for a while, but results I haven't been able to get until recently. So there's an interesting thing about it. This is so-called Hilbert's 24th problem, which he just jotted down in his notebook, and nobody knew about it because he didn't mention it at the 1900 Paris Congress, and he didn't publish it later on because most of his 23 problems weren't mentioned at the Congress. You can't fit 23 problems in a 1-hour lecture. So, but this one wasn't mentioned anywhere. And what it says is it asks for criteria of simplicity or proof of the greatest simplicity of certain proofs. Develop a theory of the method of proof in mathematics in general. And under a given set of conditions, there can be but one simplest proof. Okay? Now, where does Picasso come into the story? Well, in his first Parisian diary, which was published in 1949 as Strahlungen, Ernst Jünger relates a statement that Pablo Picasso made to him during a visit on July 22nd, 1942. He said, "My paintings would have the same effect if, upon completion, I were to enwrap them and seal them without showing them. For what we are dealing with are manifestations of an immediate kind." What's the connection between this and 24th problem? This 24th problem is exactly what Picasso spoke about hypothetically. Hilbert has really enwrapped them and sealed them without showing anything. Did the 24th problem have the same effect on the world as if it were? The answer is yes. So it came to the attention of the public, so it was unwrapped 100 years later by Rüdiger Thiele in a paper in the American Mathematical Monthly, more than 100 years later, actually. So, but its influence was considerable without ever having been published. The theory of the method of proof has been dealt with by Gensen in 1936, where we have natural deduction, sequent calculus, and so on, the analysis of what is proof. Now, the simplicity part has also been dealt with. It is much more difficult, obviously, to get results in that area. The given set of conditions is kind of hard to figure out. And let's see what the kind of problems are. So if you have a statement sigma from a subset sigma prime of axioms in a given system sigma, then it's preferable to using than to get it from a subset than to get it from the whole thing. But the problem is that if you use a subset, then your proof will become perhaps much longer and much more complicated. So how do you reconcile these? Should you seek a minimal set of assumptions from which sigma can be proved, or should you seek the shortest proof that you can get? So what counts as assumption, first of all? He speaks about, you know, assumptions and things, but what counts as it? Is there a list of acceptable axioms that we are allowed to choose to, or is any statement that looks simple enough allowed to be called an axiom? And should we not look at the simplest possible, when we look at the simplest possible proof, shouldn't we look at the simplest or most appropriate given set of conditions? So the question is extraordinarily complicated because of the not defining of where should this proof be happening. Here's another quote from what Hilbert wrote down. He said, quite generally, if there are two proofs for a theorem, you must keep going until you have derived each from the other, or until it becomes quite evident what variant conditions and aids have been used in the two proofs. Given two routes, it is not right to take either of these two or to look for a third. It is necessary to investigate the area lying between the two routes. That's very complicated in practical cases. We've seen already in the past lectures the example of the concurrence of the medians of a triangle. We can prove it from statements about point reflection, but those statements work only in places that have a Euclidean metric. The statements are very simple. The proof is not that complicated, but is this the right setting? The other setting was metric planes, this very general theory of absolute geometry. The two theories were incomparable. In other words, the people in the absolute geometry, in the metric plane story, do know what point reflections are, and they can tell you that the axioms that the other guys are using is not true here, because it's an axiom that is true only in the Euclidean metric setting. So, but the people in the point reflection world have no idea what these other people are talking about, because they're talking about line reflections. There's no line reflection in the other one. So the two languages do not communicate. So if we compare them, then we compare them from our knowledge of history, of what it is to be absolute geometry and all these things. So we think that the proof from metric planes is more appropriate or more valuable because it avoids reference to the nature of the metric which the other one makes. So this is informed by our knowledge of history of geometry and so on. There's nothing formal that tells you this story. So the decision which one is the appropriate one, which one uses the right set of conditions, cannot be done in an automatic manner. It is an extraordinarily deep thing to say that this is better than the other. I mean, the proof with point reflection uses 3 axioms, very short. All axioms are equations. The other one is rather complicated. It's a universal existential axiom system. It has many axioms, says many difficult things. If you look at them formally, you would say, oh, I surely prefer the one in point reflection. So you have to look much deeper into what they're saying than this. But this much deeper is, you need to know what geometry is all about. Whereas Hilbert wanted a way that is universal, that works for any proof, not a specific proof where you have to be looking at these things. Now, why did it have an effect nevertheless? Although nobody knew about the 24th problem. Well, Hans Brandes in 1905, which is very shortly after, already produced a dissertation doing exactly that. His concern was the number of times the plane congruence axiom needs to be used in any proof by decomposition of the Pythagorean theorem from Hilbert's axiom system for plane geometry, in which you don't use the continuity axioms. What do we mean by proof of by decomposition? It's a proof in which you take the squares that you built on the sides of your right triangle and on the hypotenuse, and you split them into triangles. You triangulate them, each of these, and you show that the corresponding triangles are congruent. It turns out that the minimum number of uses of the plane congruence axiom. The plane congruence axiom is something like the side angle side congruence axiom in Hilbert, together with the fact that the triangle is congruent to itself. You need both these because sometimes the triangle doesn't move. It's common to these two, so you don't need that. So you need 7 uses if you want to prove the Pythagorean theorem by decompositions in a proof by decomposition. Then you have to use the plane congruence axiom at least 7 times. Why? Because he was able to prove in his dissertation that you can't do it with fewer than 7 triangles in your triangulation. In fact, the ideal situation is the one presented in this picture. Yeah. So what's going on in this picture? Well, you got a right triangle, which is the one here in the corner here. This, and this, right? This is the square over the hypotenuse. This is the square over one side, yeah? And this is the square over the other side. Yeah? I mean, it's not really there, but if this is the same as that, then it's, you know, the same thing. And here you see the triangles that you decompose it into. You need to decompose this, yeah? You have the one is the same as this is the same as that is the same as that, and then you have 2 which is common and then 5 is also common. It's common to this and common to that. But the 5, you have to split it into 2, right? Because you don't know what a common quadrilateral is. You have to triangulate. Everything is in triangles, right? Okay, so there you have it. What do we have? A criterion of simplicity of proofs is how many times do you have to use a statement in a proof of another statement? So here we get the idea of a proof simplicity thing. If you have a fixed set of axioms, so we fixed ourselves now on the conditions and all that story. So we live in a fixed world. The set of axioms have been decided upon. We don't question them. Usually what you would call a simple proof would be a short proof. But what does a short proof mean? It means that you have few lines, but what do you do in those lines? Well, you use axioms. Okay, so what makes a proof long? Well, you use some axiom many times. Well, so multiple uses of an axiom are the place where you should focus then to get short proofs. Well, now you need a human being to tell you which axiom is expensive in this world. And in this case, Hans Brandes decided that the plane congruence axiom is the one that is heavy. The other ones, what would they be? I mean, betweenus axioms, well, they're not really the heavy lifting part. And what else? That congruence is an equivalence relation? Well, that's not really interesting. So what is it? It's the plane congruence. It's the how many triangles are you going to compare? So that's where you should focus on the minimum. And so he got this first proof of a proof simplicity. And oddly enough, the Pythagorean theorem appears in this wrapped painting by Hilbert. Where is it? I don't have it. I thought I wrote it. He refers to it somewhere. No, I didn't write it. In these notes in the book, he refers to the Pythagorean theorem, and Hans Brandes answers that. So actually, there is a story in this. So Max Dehn, also not having read anything, his Dr. Vater's 24th problem, writes in 31, at least how often must one use the configuration theorem S in order to derive from it the configuration theorem T? So exactly Brandes' problem. One such example is Pappus and Desargues. We know since Hessenberg's 1905 proof that 3 times Pappus implies Desargues. Is that the minimum number of times? The answer is yes. And it came to me in 2018. Here is Desargues. You have 2 triangles, the A triangle, A1, A2, A3, the B triangle, B1, B2, B3. If you join the A's and the B's, then you're getting to these 3 lines are concurrent. Then now you look at the intersections of these corresponding sides. You get these C points. What Desargues says is that these C points lie on a line. And then you have Pappus, which says something similar, that if you have these 3 and you join them like in the picture, then these 3 intersection points are also on the line. Also, we have seen in the past that Veblen proved that outer Pasch implies inner Pasch. Outer Pasch being this story here. If you have the 5 solid points, then there exists an F that is exactly as in the picture. And here it says if you have these 5 solid points, then there is an F that is as in the picture. And it turns out you need to apply outer Pasch 3 times, just as in Veblen's proof. These are obviously lucky situations that we could prove that this is the minimum number of times. What do you do if you need to apply IP, say 9 times to get the midpoint of a segment, to prove that the segment has a midpoint? Then the thing is much worse, obviously. Because, you know, showing that you can't do it with 8 or fewer times, it's much more complicated than 2 or fewer times. You know? The way we had it in the Pappus implies Desart story or in the outer Pasch, inner Pasch. And that's the story. I mean, it's a huge field. It's very hard to produce results in this field. I mean, to prove that a certain axiom has to be used that many times. We're very far from having a general solution to it, but people have been concerned about this in the absence of the 24th problem being published. And as I said, Hilbert even referred to the Pythagorean theorem, and Hans Brandes did not. Well, that's it for today.